There are billions of habitable planets in our galaxy alone.
The James Webb Space Telescope is shaping up to be one of the most significant breakthroughs for humankind regarding space observation. Being far more powerful than all other space telescopes ever launched by humans, the scientific community has high hopes. It will enable them to study very distant objects in space as they have never been able to. One of the objects the JWST will study is Proxima b, to see whether artificial lights are coming from the planet. Yes, you heard right. Scientists want to know if the lights coming from Proxima b are due to aliens. What will the JWST see when it focuses on the exoplanet, and how does it affect you? Join us as we dive into the James Webb Artificial Lights discovery on Proxima b that changes everything. Are we alone in the universe? While that question may be tantalizing and produce different answers from different responders, an even more difficult question to answer is where to look for intelligent life outside the Earth in the universe. Many planets have been suggested as good places to search, but the best so far, according to scientists, is an exoplanet named Proxima b, and that is due to terrifying discoveries made on the planet. Why are scientists focusing on Proxima b? Where is it located? What scary things have they found on the planet? And how will the new James Webb Space Telescope confirm the terrifying discoveries on Proxima b? When you look up at the sky at night, you will see stars bright against the dark night sky. What may not be visible to you are the planets that orbit these stars. These planets, known as exoplanets because they're outside the solar system, are too far away to be seen by the naked eye. But there is another reason why they are challenging to spot even with telescopes, which you will see in this video. However, these distant planets may be hiding a secret: alien life. Some of these exoplanets are located where scientists suspect it allows them to host life. There has been a lot of interest in these planets, but a lack of equipment has hampered researchers' ability to study them. However, there is a new kid on the block: the new and powerful James Webb Space Telescope. In the search for life outside the Earth, scientists are not too naive to expect to pick up live footage of aliens walking about, even though that would have been a decidedly exciting find. What they do is look for clues of life on these planets. So what exactly tells scientists that living organisms or potentially aliens live on a planet? Since its discovery, scientists have focused their search for alien life on Proxima b, whose parent star, Proxima Centauri, is part of an odd stellar trio that astronomers are still struggling to understand. The other two stars are binary, meaning that they orbit a common center of gravity. All three are known together as Alpha Centauri. Astronomers aren't really sure whether Proxima Centauri is gravitationally bound to the other pair in some type of orbit or if it is just passing by. You can easily spot Alpha Centauri without a telescope. This is because the three binary stars combine to make the third brightest star in the sky. Proxima is slightly closer to Earth than the other two. It is 4.22 light-years away, as opposed to Alpha Centauri's 4.37 light-years. However, because it's also much smaller and dimmer than the other two stars, you can't easily see Proxima. It is a red dwarf and it's too faint to see with the naked eye. Proxima b's orbit around Proxima's star is very small. The planet orbits its parent star at a distance of 4.6 million miles or 7.5 million kilometers, which is only 5% of the distance between Earth and the Sun. The Sun is 93 million miles or about 150 million kilometers away from our planet. And while our Sun is a bright, massive star in Proxima b's sky, people on Earth need special equipment to be able to see Proxima Centauri. Proxima b is located in the middle of Proxima's habitable zone, a place that allows liquid water to theoretically form on the planet. You would have noticed that compared to our Sun, Proxima Centauri's habitable zone is extremely close to its parent star. The reason is that Proxima is much cooler than the Sun. Proxima b is the closest Earth-like exoplanet scientists have ever found, just over 4 light-years away. But that does not mean we can send astronauts to it anytime soon or ever. Traveling to Proxima b with the current technology can take thousands of years, so no emissaries from Earth are heading in that direction yet. Proxima b does not orbit its star in front of us. This means if you were to look at Proxima Centauri head-on, you wouldn't see Proxima b, as it does not pass in front of its star from our perspective. This makes predicting its orbit difficult, and astronomers do not know whether or not Proxima b has a nearly circular or highly elliptical orbit. Astronomers also say if Proxima b did form in its current orbit, it means the planet has not always existed within the habitable zone. Proxima Centauri would have been hotter before becoming a main sequence star, so Proxima b may have formed too close to its star and stayed there for many millions of years. Detecting exoplanets like Proxima b is an extreme sport. This is because they are hard to observe, and scientists have to be very creative to spot them. The first confirmation of an exoplanet was in 1995, but scientists estimate there are trillions of them in our galaxy alone. In fact, they may outnumber stars significantly. Many of them are suspected to be the size of the Earth. The exoplanet discovered in 1995, known as 51 Pegasi b, was a hot gas giant believed to be about half the size of Jupiter. It tugged so hard on its parent star as it raced around it in a 4-day orbit that it caused its star to wobble so much that telescopes on Earth were able to notice, but that was after astronomers knew what to look for. The method used to describe 51 Pegasi b is known as the wobble method. It measures changes in a star's radial velocity. The wavelengths of starlight are alternately squeezed and stretched as a star moves slightly closer, then slightly farther away from us. Those gyrations are caused by gravitational tugs, this way and that, from orbiting planets. Another method of detecting exoplanets is the transit method. It was made popular by the Kepler telescope and involved the telescope fixing its gaze on a part of the sky for years. The patch of the sky that Kepler focused on contained about 150,000 stars. It was waiting to spot tiny dips in the amount of light coming from individual stars caused by planets crossing in front of them. The time the dip takes and the mass of the anchoring star can be used to calculate the size of the planet. Another method of discovering exoplanets is the transit spectroscopy, which analyzes the light coming from the stars that have passed through an exoplanet. The light can reveal the composition of the planet's atmosphere, just like you can detect the composition of light by passing it through a prism. It will reveal info like the molecules present in the atmosphere. Another method is gravitational microlensing, which uses the ability of gravity to bend the light coming from a star. However, with the launch of the James Webb Space Telescope, scientists now have the best equipment ever for discovering exoplanets. In fact, searching exoplanets for alien life is one of the main uses of the JWST. The powerful telescope was launched late last year at a cost of $10 billion, an unbelievable increase from the $1 billion initially budgeted for it. It was developed by NASA in conjunction with the European Space Agency and the Canadian Space Agency, with input from more than 300 organizations, including universities. The start of the JWST is the Mirror. At 21.3 feet or 6.5 meters across, it's the largest mirror ever launched to space. It is significantly larger than the 7.8 feet or 2.4 meters disk that is the centerpiece of the Hubble. JWST's mirror, also called the Optical Telescope Element (OTE), is made from beryllium coated with gold. It's fashioned from 18 hexagonal sections, each one the size of a large table. It uses more than 100 motors to reposition the mirrors to focus on objects. JWST observes in long red wavelengths, mostly in the infrared. Scientists will rely on this capability to look at objects farther from us. Light from these objects is redshifted into longer wavelengths. JWST carries 4 instruments designed specifically to very sensitively detect infrared signals. The instruments are housed in a spacecraft bus, which is actually a box made primarily of graphite composite. It also contains JWST's thrusters, computer and communications equipment. In essence, the bus is JWST's heart and brain. The bus is protected by a massive sun shield and equipped with a cryocooler that uses helium to keep its components at a frigid -393 degrees Fahrenheit or -236 degrees Celsius. This is necessary because heat can interfere with the operation of the components in the bus. A little heat can throw off the mirror. The JWST launched with the sun shield folded as there was no other way to contain it on the launch rocket, similar to how the mirror was folded. Within the first 2 weeks of the observatory's flight to its permanent position, the sunshield fully opened to cover the length of a tennis court. The sunshield consists of 5 layers of a polymer called Kaplan E, sandwiched between aluminium and silicon to reflect sunlight and heat away from the observatory. As the JWST orbits the sun sunshield always stands between the mirror and the sun's direction. One method Webb will use for studying exoplanets for evidence of life is the transit method. Webb will also carry coronagraphs to enable direct imaging of exoplanets near bright stars. The image of an exoplanet would just be a spot, not a grand panorama, but by using the JWST to study that spot, scientists will learn more about it, including its color, differences between winter and summer, vegetation, rotation, weather, and much more. Of course, scientists try to listen for signals in light or radio wavelengths that may be coming from technologically advanced alien life, as the Search for Extraterrestrial Intelligence Institute SETI explains. The astronomers at the institute have been using Allen Telescope array of 42 radio antennas to listen for signals over a range of radio frequencies, tuned to hear the regions around 20,000 red dwarf stars that are closest to Earth. But that is just one part of the search. For an alien-seeking scientist, life means any living form, including microbes. This is because even the smallest microbe on a distant planet could still send a chemical signal that can be picked up by our sophisticated telescopes. This could be the result of atmospheric gases that might not have been there if there was no life present. One of such gases is oxygen, which could suggest life on a planet. There are other gases or substances like water which scientists watch out for in their search for evidence of life, but they have to be cautious because the presence of these substances may have other explanations apart from life. Now, why are astronomers interested in the Proxima b exoplanet? To understand this, you need to know its location. Our nearest neighboring star is the Proxima Centauri, located about 4 light-years away. Just like our Sun, Proxima Centauri has its own set of planets orbiting it. One of the planets is the Proxima b. This exoplanet was discovered in 2016 and has intrigued scientists ever since then. Scientists have also discovered Proxima c and Proxima d, although Proxima d is still awaiting confirmation. However, much of the attention has been on Proxima b for good reasons. Because the planet orbits right in the middle of its star's habitable zone, it's possible that liquid water and potentially even life could exist there. Because of its Earth-like mass, scientists believe that not only could liquid water exist on Proxima b, it could also be a rocky, terrestrial planet similar to Earth. Proxima b orbits around a star that, while close to our solar system, is also much dimmer and much less massive than our Sun. The exoplanet is tidally locked and in synchronous rotation with its star, meaning that one side is always facing the star and one is always facing away, a light side and a dark side. In addition, it's unclear if Proxima b has an atmosphere. However, if Proxima b has an atmosphere, the simple ingredients, water, carbon dioxide, and rock that are needed for the formation of biochemical cycles that we call life could all be present and interacting on the planet's surface. The planet lies very close to its star, completing one orbit every 11 Earth days. The temperature on the surface of the planet could be between -90 degrees and 30 degrees Celsius, or -130 and 86 Fahrenheit. Astronomers first discovered Proxima Centauri b in 2016 using an older spectrograph called HARPS. However, the discovery has been confirmed by the newer spectrograph Espresso, which is the most accurate in the world. Any doubts were cleared after Espresso acquired a total of 63 spectroscopic observations of Proxima Centauri in a single year. Proxima b is similar to the Earth in many ways. First is the size. In fact, after numerous studies, scientists concluded that Proxima b is more Earth-like than earlier thought. They discovered that Proxima b is just 17% larger than our own planet. Previously, the conclusion was Proxima b was about 1.3 times heavier than the Earth. If you were to live on Proxima b, you would age significantly faster than your peers back on Earth because this planet completes an orbit around its Sun in just 11.2 days using Earth measurements. Scientists say Proxima b is tidally locked to the Sun it orbits, meaning only one side is always facing the star, creating perpetually dark and bright sides. This is the same with the Moon and the Earth, as we can only see one side of the satellite. Proxima b is part of a 3-star system, meaning there are 2 other planets orbiting the same star. However, the 2 other planets are more difficult to study because they do not transit in front of Proxima Centauri. In fact, they were detected using the radial velocity method, where the planet's gravity causes a slight wobble in the star's motion. Another similarity between our Earth and Proxima b is the location of the 2 relative to their respective stars. Both of them inhabit the Goldilocks zone of their individual stars. The Goldilocks zone refers to the part of the area surrounding a star that can possibly allow life to survive. While Proxima b orbits its star at a distance that is 1/12 of the Earth's distance from its own Sun, Proxima b gets about 2/3 of the energy that the Earth gets. This is due to the smaller brightness of the star and the smaller distance between the two bodies. This is why scientists suspected there is life on Proxima b. Orbiting in the Goldilocks zone means there is the possibility of water on the planet, and it is not just water but liquid water which is essential to life. While visible and infrared light just warm the planet, high-energy radiation or X-rays and extreme UV and particles are a threat to the gases and liquids, volatiles as a whole, as they can be eroded away and escape to space. Proxima b receives a significantly higher amount of such radiation compared to Earth, and therefore it is crucial to assess whether the planet has been able to maintain its water and gases in general over the course of the 5 billion years of history since it was born. Astronomers have used the most advanced tools and observations available today to drill into the history of Proxima b as a planet. This was aimed at determining the amount of gases and liquids that could still be on the planet's surface. They discovered that currently Proxima b gets 60 times more high-energy radiation than the Earth, and that the total from the time of formation is about 7 to 16 times higher. This conclusion was because the Earth was also irradiated more strongly in the past, long before we got here. Scientists don't know for sure the amount of water Proxima b had initially, but their calculations have shown that Proxima b could have lost about one ocean's worth of water due to the early irradiation in the first 100 to 200 million years after formation. What happened after that period is still under investigation. Perhaps this Earth-like planet continued to lose significant amounts of atmospheric gases, or perhaps it's been able to keep most of its atmosphere and preserve liquid water on the surface, making it hospitable to life as we know it. Scientists have even discovered where most of the water on Proxima b might be located, which would be handy if one day you might find yourself stranded on the planet. By examining the possible climates using a sophisticated 3D model and exploring a wide variety of atmospheric compositions and water inventories, it was discovered that liquid water might be present over the surface of the planet in the sunniest regions, either in an area in the hemisphere of the planet facing the star or in a tropical belt. What if aliens live on Proxima b? If that is the case, there is speculation that its improbable life could develop on the day side due to a constant stream of intense radiation from its host star. The reason is that Proxima b orbits just 4.5 million miles out, or about a tenth of the distance Mercury is from the Sun at its closest point. Radio signals have already been detected from the area around Proxima b. However, radio astronomers believe this was likely just interference from natural sources. So because the side of the exoplanet that is free from radiation is always dark, any civilization inhabiting the exoplanet may have to deploy powerful mirrors or require very bright LED-style lights to illuminate their cities. This can help us detect them using the right tool. This is why a team that includes Harvard astronomer Avi Loeb has suggested that the JWST can be configured to spot evidence of LED light on the planet Proxima b. They suggest that using the near-infrared instrument on the James Webb telescope and looking for the telltale signs of LED light waves in the light from the planet and its host star, they will be able to detect this artificial light if it exists. The team has investigated whether artificial lights could be detected on the dark side of Proxima b by computing light curves from the planet and its host star. These scientists considered two different scenarios: artificial illumination with the same spectrum as commonly used LEDs on Earth, and a narrower spectrum that leads to the same proportion of light as the total artificial illumination on Earth. They discovered the JWST would be able to detect LED-type artificial lights, making up 5% of stellar power. If James Webb is able to detect the narrowband light that is reminiscent of LED bulbs, it will be because it will be able to characterize the atmosphere of the planet. This will allow researchers to use instruments on the observatory to detect how much energy transport occurs on the planet and then perform calculations of light curves to determine whether they match those of an LED light source or not. To come to the conclusion that it may be able to detect artificial light, Loeb and colleagues use the JWST Exposure Time Calculator. This tool allows astronomers to predict what can be detected in any given time period based on predefined settings before the observatory launches. It allowed them to determine the possibility of detecting different flux values and detecting those with a wavelength that matches artificial light levels that should be expected from a civilization forced to live in permanent darkness. In that case, the lights shining onto the permanent night side should be extremely powerful and thus more likely to be detected with JWST. The JWST will be able to show the existence of artificial illumination for standard LEDs 500 times more powerful than those currently found on Earth's, and for artificial illumination of similar magnitude to Earth's. The discoveries on Proxima b are significant for many reasons. For one, we know that there are tons of planets in the universe. In fact, in the Milky Way galaxy alone, there are quadrillions of planets. Every single star has at least a planet orbiting it, as far as we know based on statistics. What this is saying is that the possibility of finding a potentially habitable planet like Proxima b is high. Proxima b may one day receive visitors from the Earth, although it will most likely be an emissary and not humans. Scientists and engineers announced the $100 million Breakthrough Starshot project, which aims to develop the technology required to accelerate tiny, sail-equipped nanocraft to 20% the speed of light using powerful lasers. Take note of the name Breakthrough because you will hear more about it later in this video. Breakthrough Starshot team members said they hope to launch flotillas of such postage stamp-sized probes to Alpha Centauri eventually. Spacecraft traveling at 20% of the speed of light could make the trip to Alpha Centauri in about 2 decades, instead of thousands of years for conventionally powered probes. When the Breakthrough spacecraft arrive at Proxima b, will they find aliens waiting for them? Turns out we have been receiving signals emanating from Proxima Centauri, which raises many possibilities. It all started with a strange signal picked up by the 64-meter Parkes radio telescope in Australia while it was observing Proxima Centauri. Astronomers were using Parkes to catch radio emissions from powerful flares shooting off the star. The detection was made by a $100 million project called Breakthrough Listen, led by Andrew Simeon from the University of California, Berkeley, and funded by tech billionaire Yuri Milner under the umbrella of Milner's Breakthrough Initiatives. The goal of this multi-year endeavor, which began in 2015 with a star-studded announcement attended by Stephen Hawking and other space science luminaries, is to buy observing time on radio telescopes around the world to search the skies for evidence of technological civilizations. Their pursuit is more commonly known as the Search for Extraterrestrial Intelligence, SETI. Using Parkes, the astronomers had observed the star for 26 hours as part of their stellar flare study. But as is routine within the Breakthrough Listen project, they also flagged the resulting data for a later look to seek out any candidate SETI signals. The task fell to a young intern in Simeon's SETI program at Berkeley, Shane Smith, an undergraduate student at Hillsdale College. Smith began sifting through the data until he stumbled upon the curious narrow-band emission, needle-sharp at 982.002 MHz, hidden in plain view in the Proxima Centauri observations. From there, things happened fast. It's the most exciting signal that we've found in the Breakthrough Listen project because we haven't had a signal jump through this many of our filters before, says Sophia Sheikh from Penn State University, who helmed the subsequent analysis of the signal for Breakthrough Listen. Soon the team began calling the signal by a more formal name, BLC-1, or Breakthrough Listen Candidate 1. Although the press reports are unclear on exactly how and when Parkes detected the signal, it apparently showed up during 5 30-minute periods over several days, all while the telescope was pointing directly at Proxima. Breakthrough Listen uses a technique called nodding, where the telescope will spend a period looking at a target and then an equivalent period looking elsewhere in the sky to check that any potential signal is truly coming from the target. In 5 of the 30-minute observations over about 3 hours, we see this thing come back, Sheikh says, a hint that the signal indeed originated from Proxima Centauri or some other deep space source in that part of the sky before making its way to Earth. Notably, when the telescope was turned away from the star, the signal vanished. Ultimately, the signal's origin appears tightly constrained within a 16-foot wide circle, roughly half the size of the full moon around Proxima Centauri on the sky. Breakthrough Listen employs software filters capable of rejecting the cacophony of signals originating from Earth or Earth-orbiting satellites to isolate those coming from deep space. But this transmission was unlike anything the project had previously encountered. Team leader Andrew Simeon told Scientific American that it had some particular properties that caused it to pass many of their checks and struggled to explain it. Most curiously, it occupies a very narrow band of the radio spectrum, 982 MHz specifically, which is a region typically bereft of transmissions from human-made satellites and spacecraft. We don't know of any natural way to compress electromagnetic energy into a single bin in frequency, such as this one, Samian says. Perhaps, he says, some as-yet unknown exotic quirk of plasma physics could be a natural explanation for the tantalizingly concentrated radio waves. Speaking on the significance of the discovery, Jason Wright, a SETI-centric astronomer at Penn State University in Pennsylvania, said, "If you see such a signal and it's not coming from the surface of Earth, you know you have detected extraterrestrial technology." Let's hear what you think of alien life on Proxima b.